Okay, so this is the start of lecture 13. I'm not sure how many videos I'll be making because there are a number of parts to this. So we'll just call this part 1. And I'm going to start out talking about solutions, aqueous solutions specifically. And we're going to detail from there. Okay, forgot what I was going to say. Let's go to the slides. So in general, I'll be defining solutions, but specifically we're from here forward, with the exception of the very last set of lectures, redox, we're going to be talking about aqueous solutions. And these very specific type of solutions, it's in water. So aqueous, and we show this by putting this as the physical state. So you have solid, liquid, gas in an equation, but you also have AQ, aqueous. That literally means in water. So if you see that in a reaction equation, that means you have dissolved that substance in water. So it's a very important designation. And it actually says a lot, which is what this series of videos will be covering. So something dissolved in water can behave in any number of ways. But first, let's go step back and just talk about what is a solution, because it doesn't have to be aqueous necessarily. Solutions are mixtures. Solutions are homogeneous mixtures. So you come down here, no matter where you sample a solution, you are going to get identical composition. Concentration of everything will be the same. So it's homogeneous. All right, these are terms you do need to know. The solution, of course, is a homogeneous mixture. So if I ask you true or false, a heterogeneous mixture could be a solution, you would say no, that's false. It must be homogeneous. Otherwise, it's just a mixture, it's not a solution. You have your solute, which is what's being dissolved. Let me go back to the whiteboard a minute. So the solute is what's being dissolved. It's dissolved in the solvent. Okay. So U, the solute, is being dissolved in the V. All right, because that's easy to get confused. You'll hear me do it, unfortunately. So the U is getting dissolved in the V. The solute is getting dissolved in the solvent, right? You've got this big old batch of solvent, and you've got all the solute dissolved in it. Looks like birds. So U is getting dissolved in V. Solute is dissolved in the solvent. Back to slides. So that's for any solution. If the solvent is water, then we call that an aqueous solution. And again, that's the AQ designation. The concentration is the amount of solute per unit of solution. And this is written this way because the terms used, there are a number of different ways to write this. So let's go to this table here. Amount of solute, where's the table? Okay, it's further down than I thought. There we go. So amount of solute per unit of solution. Here are all the different ways we can say that. And we do, depending on what area you are using this. There's specific reasons to use each. So we say something percent by mass. It's the amount of solute is in grams. Amount of solution is in grams. If we talk about percent by volume, you know, again, you get this often in the liquor store. You have something that's 40% alcohol. It's 40 mils of alcohol per 100 mils of solution. You have a mass volume percent. Your amount of solute can be grams with mass, right, over a volume of solution. These are all in percentages. You can have a parts per million or a parts per billion. This is generally used in toxicology, perhaps sometimes in medicines, but usually more in toxicology. It's how we define something that's poisonous in trace amounts, toxic in trace amounts. And so we say parts per million or billion. And the two most common for aqueous, molality and molarity. You will learn most of these in Chem 1, particularly molality. So here we're going to be working with molarity, all right? So this is just to show you that these exist, but our friend here is the molarity, moles of solute per liters of solution. Okay, but down back. So that's our concentration. So why do solutions form? Where's my eraser? Why does something dissolve? Why does a solute dissolve in a solvent? It has to do with intermolecular forces. And again, in Chem 1, you'll get into this in detail, and it's actually pretty cool because that determines so much. But if your forces, your intermolecular forces between the attraction between solvent and your solute are strong enough, then the solvent surrounds your solute. So in water, for example, with sodium chloride, the water surrounds each ion, the water molecule. So it's completely surrounded. It's called solvated. It's surrounded by a solvent, solvated. We call that dissolved. Anything that is soluble in, let's just say water, we call that dissolved. So let me go to the whiteboard a minute. What happens when something dissolves? Because this is what this next series of slides or lectures will be about. When you put something in, I'm going to stick with water just to keep it simple. So just understand that everything I say about water as a solvent can apply to other solvents as well. Alcohol, propane, you know, but let's just stick with water. So when you put something in water, one of three things will happen. It will dissolve, and we call that soluble. Okay. We have something called partially soluble, which we're not really going to use here, but I want you to be aware of it. You'll see it in one of the tables, and it dissolves a little. So this dissolves completely. If something is partially soluble, it dissolves a little, but not much. Right, the rest of it's insoluble. And then you have insoluble, does not dissolve. You put a rock in water, it's insoluble. You put chalk in water, it does not dissolve, right? It just floats around in there. So that's insoluble. Sugar, salt, any of these are soluble. Kool-Aid is soluble. Partially soluble is something that dissolves a little, but you still have some left. So these are the three. And like I said, we're not really going to use partially soluble, but just be aware that that exists. Mostly we're going to look at soluble and insoluble in this class. So what does it mean to dissolve? This is the next thing. Okay, so these are some terms that you need to know and that we're going to break down into great detail how you use these terms in chemical equations, chemical reactions. And again, it's going to be a whole series of videos. If you have something that is soluble, what happens to it? It dissolves completely. Okay, well, what does that mean? It doesn't always mean the same thing. You can have it dissociates. That means it breaks apart into its parts and pieces. This is what ions, ionic compound. okay? It can ionize. And this means you start with a molecule and you end up with an ion. So dissociates, you have an ionic compound that you get ions. But it ionized, and I'm just introducing you to these terms right now. We're going to get into detail. This is acid-base chemistry, and you start with a molecule, a covalent molecule, and you actually create ions. And this is a chemical reaction with water. And the third is it simply dissolves. This means it does not break apart into its individual parts and pieces like an ionic compound breaks apart into its individual ions. This will break apart into a sodium and a chloride ion surrounded by water. Your individual molecule, alcohol, gets surrounded by water, but it does not break up into its constituent carbons and oxygens and hydrogens. So each ion is surrounded by water, right? I'm going to show you some videos of this. But here, the entire molecule, an individual molecule is surrounded by water. And this is usually alcohols and sugars are the examples we're going to give you most of all. All right, I'm going to show you some videos, but we'll just go back a little bit more to why does dissolving happen. So something is soluble and it dissolves. That can mean one of three things. It can either dissociate, and that's your ionic compounds. It can ionize, that's our acid-base chemistry. Or it can simply dissolve. That's what dissolution is. Just dissolves, but nothing else. So the individual molecule is surrounded by water. So back to the slides. And it's these intermolecular forces between water and the ion or the molecule that creates this. And an acid-base is actually a chemical reaction. So when we are talking specifically about water, it has to do with the polarity. Remember, we learned about polarity last week. You have a dipole moment. You have an area of, this is one oxygen and two hydrogens, of the molecule that is more negative, has a negative dipole moment. We use, that's our designation. The electrons are more concentrated, or the electron cloud is more concentrated around the oxygen end than at the hydrogen ends. So you get a more positive region and a more negative region, and that interaction creates the dissolving. So if you have, remember, ions exist in complexes, in crystals. So the water, is there a picture of it here? No. All right, here we go. So the water molecule goes up to that complex, that crystal, and the negative end, the oxygen end, will be attracted to the positive charge of the sodium. And it surrounds it, it pulls away a sodium ion from the crystal. By the same token, the positive ends of the hydrogen are attracted to the negative charge on the chlorine. So it will actually pull away the chlorine ion, all right, from this crystal. Because remember, sodium chloride exists in a crystal by electrostatic forces only. There's no sharing of electrons going on. And so they can be pulled away. And because you have so many water molecules surrounding that chlorine, just one by itself can't do it. But when you have so many, it completely surrounds it. That's sufficient to disrupt the attraction between the sodium and the chloride ions. And so these are going to pull away the individual ions. So that is dissociation. It's dissociating into its separate parts. Whereas when you have a molecule, like a sugar molecule, for example, it surrounds the entire molecule. It's not strong enough to break this sharing, because sugar molecules, alcohol, that's covalent bonding. Those electrons are being shared. And so the water interactions with the molecule are strong enough to surround it and separate it into the individual molecule, but not individual atoms. So I want to show you two videos. One is showing salt in water and this dissociation process, and the other is going to show sugar in water, and that's simply dissolving, where the molecule is surrounded, but it's still a sugar molecule. And whereas the salt becomes, oops, come on, individual ions. Okay, this one's kind of loud for some reason. No, try to get it bigger. Nope. Sorry, guys. There we go. Okay, so here's the first one.
When an ionic substance such as sodium chloride is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens. When an ionic substance such as sodium...
Okay, so notice that that was pulling away the individual ions, and the more you pull it away, the more are exposed further in, until ultimately all of them are separated from the crystal, and they are completely, all the ions are separated and surrounded by water. Whereas this is the sugar. And notice when in this one, the sugar molecules are separated, but they still are retained as individual molecules. They are not separated into constituent parts and pieces. For some reason, they're using purple sugar. See, that's an individual sugar molecule. These are being surrounded by the water molecules and pulled apart from the crystal. But they are staying a complete sugar molecule. Okay. So that second one was dissolution, dissolve, dissolution. But the first one, yes, it was dissolution. Anything that dissolves is dissolution. Dissolution, out of solution, or into solution. But the ionic compounds also dissociate. They break apart. And this is all because of the intermolecular attractions with water, because of the polarity, and either the individual ions or the molecules. So we're going to get further into the other types of dissolution and ionization, but right now the rest of this lecture is just completely focused on dissociation and how we write these equations. When you write a dissociation equation, it's called ionic dissociation. An ionic solid dissociates into individual ions in the aqueous state. First of all, I want you to notice there is no H2O in this equation. You do not put H2O in aqueous equations unless they are actively involved in the chemistry. If you can write the product without H2O, don't put it in the reactant side. Very important. The only time you put it in is the acid base, because then you cannot write the product without an H2O here. But here, how do we know there's H2O? Because it has aqueous. So you have sodium chloride solid. You have crystals of salt. You dump them into water. They separate into individual sodium ions and chloride ions, and we know they're surrounded by water molecules because of the AQ. So the AQ tells us a lot. So at this point, phases are very, very important, and writing complete equations are going to be very important. So this simple little sentence is actually it tells you a tremendous amount. It tells you sodium chloride is soluble, that it dissociates completely. Okay, when you have an arrow that only moves in one direction, it's 100% to the right. It makes 100% of the product. There's nothing left of your starting material, because later we're going to see examples where we actually have a double arrow going in each direction. So when you have a single arrow, which is all we've used so far, it means it goes 100% to products. You have no reactant left at the end. So that tells us this is completely soluble. Notice you start as an S and you end up with the two ions, and we know that it's water because we use aqueous. So there's a lot of concepts in that simple little sentence. Okay, so this goes back to solubility. We can have soluble, insoluble, and then partially soluble, but we're really not going to use that this semester. How do you know something is soluble? There are some rules that you have to learn. Yes, you have to do some memorization. Most of them, however, we're going to use so frequently. There are a few main rules that you will use so frequently that it'll be easy to remember. And that is primarily this one. Sodium, potassium, and ammonium are used all the time. They are always soluble. So if you see an ionic compound and it starts with sodium, potassium, or ammonium, it's 100% soluble. That's going to be your biggest signal right there. Nitrates are soluble, bicarbonates, and chlorates. All right, so this is the group 1, right? Lithium, sodium, potassium, rubidium, cesium. So group 1, I'm looking at and remember, hydrogen is considered part of a non-metal for these kinds of categories. So any group 1, take hydrogen out of there, that you see in a compound, it's soluble. Okay. Most halides, but notice fluorine's not in this list. So group 7, fluorine or chloride ion, bromide, and iodide are soluble. But notice fluorine is not in here. It's not always. Fluoride ion is not necessarily soluble. You have some exceptions here. Sulfates are soluble, with some exceptions. I don't expect you to memorize all these exceptions. I do expect you to remember the common solubilities. And these insoluble. Most of these you're going to use so often, they'll become natural to you. Okay, the other thing I like to use, I don't know if I'm going to be able to do it with this Canvas exam when we use this or not, exam 4, but I like tables because I want you to learn to read a table. And as I get into explaining how we write these equations and how you can tell if you actually have a reaction, it goes back to, if you have as a product an insoluble compound, so I will go down here and I would say magnesium plus hydroxide, right? Ammonium, lithium, sodium, potassium, they are soluble. The only exception is lithium phosphate. So anytime you see sodium, potassium, ammonium, soluble. Look at that. So ammonium hydroxide is soluble, but what if I put it in something and there's some magnesium in there as well, and the magnesium and the hydroxide react? It's going to precipitate. It makes an insoluble compound that's going to fall out of solution. You're actually going to see it form. It's going to, we call it fall out of solution. Storm. So I want you to learn to read this table and say, when I teach you how to interpret reactions. And then I like to give questions where you have to read the table and get an answer appropriately. So this is what I like to do. So know these rules, particularly for the most common, but also I want you to learn to read the tables. Here are the rules again, but they are in written form. So we have a table form and a written form. It's the same rules, but sometimes some people find this easier to understand than a table. So you're given it in both examples. And here's the fluorides are generally insoluble. So remember, group 7, chlorine, bromine, and iodine ions. So chloride, bromide, iodide are soluble. And all of the group 1, excepting hydrogen, which doesn't belong in group 1 for this stuff. So I'm not going to get into that too much detail. Why doesn't everything dissolve? That you'll learn about in Chem 1. But again, it has to do with the intermolecular forces. Pure and simple. Okay. So this is showing what that little video showed. There's your sodium chloride salt. You put it in water. The water molecules come around and surround it and pull them apart. Now, this is an actual reaction equation. The first one I showed you before was an ionic dissociation. There was one thing on the left side, and it was a solid, sodium chloride. And we had sodium and chloride ions separately as aqueous on the right side. This is a reaction. And you're mixing two solutions together. And then you're seeing if you form a precipitate. So I'll get into this in more detail. Just notice the difference in these reaction equations right now. Okay, these are two aqueous things. You're mixing two solutions together. The previous ionic dissociation, you had one solid on the left side and ions with the aqueous designation on the right side. Different type of reactions, and we're going to get into all of that. Okay, well, I guess we're going to get into that right now. All right, I'm going to stop here and then start the second lecture. I'm going to get more specifically into these types of reactions. So the first, then we'll stop here and we'll say, lecture 13, part 1, simply introducing you to solubility, aqueous solutions, and the different things that can happen with solubility. All right, so, and then the second, lecture 13, part 2, I will get more specifically into the types of reactions you can get with soluble solutions, solutes. Okay.